First, today we will see Bode plot. So first, Bode plot is one of the well-known technique to perform stability and frequency analysis of electronic circuits and systems. This is a very useful technique. And for example, we use this in communication systems like RF communications and analog circuits. So I mentioned here stability and frequency analysis of circuits and systems. So analog circuits means, for example, you have already studied about analog filters, right? Low pass filter, high pass filter, band pass and band stop filters. In those filters, we have studied about frequency responses or frequency analysis. So I hope you remember we had two parts when we talk about frequency analysis. The first one was let me take my pen. So we had two parts of frequency analysis. One is about the frequency response. For example, in low pass filter, we have these low pass frequencies will pass. The high pass frequencies at the high pass frequencies will be stopped by the filter. So output will be 0. So this is the magnitude. So we always used in terms of dB. But in the second part of the graph, we used some kind of phase response, right? So this is the phase angle. So this is called Bode plot. So Bode plot can help you to analyze the output with respect to the amplitude in dB, decibels, and also the phase angle in degrees. Okay, and this is originally developed by Nyquist and Bode, two guys, in 1930. This idea was originally initiated by this guy called scientist called Bode. That's why we call this as a Bode plot. So we will see the basics of Bode plot with respect to frequency considerations today. First, what is the definition of frequency response? The frequency response of a system is defined as the steady state response of the system to a sinusoidal input signal. So remember, in any system, you can talk about any electronic system or electronic circuits. It can be kind of any electronic systems. For example, the well-known system for you right now is filters. So in any system, we are applying the input signal to this system. And then we are getting some kind of output. This is normal in any electronic systems. So output is not same as the input. Output is always varying in amplitude, or its output is also varying in phase angle, and also the output is varying in frequency. So it's really depending upon the system property or system characteristics. The output is different from the input. It can be varied only in amplitude, phase and frequency may be the same, or in some systems, everything, amplitude, phase, frequency, everything got changed at the output. So now in this kind of situations, we need to analyze this output, how this output got affected by these system characteristics. Okay, so the sinusoidal is a unique input signal and analyzing the resulting output signal for a linear system. So remember, linear system, linear time invariant system or linear time variant system. So we talk about different terms. Linear system means what? So whatever the input you are giving to the system, at the output will just vary linearly. For example, like this one, the output is just varying linearly. Okay, so linear system. So whenever you apply the input to this linear system, we are getting some kind of output. We need to do analysis mathematically. So we need to model transfer functions from physical data. So this transfer function also we have studied already a little bit. So transfer function means what? VO divided by V in, output divided by input. voltage. Output voltage divided by input voltage. It's called a transfer function or gain. Gain A. Okay. So we need to model this transfer function from the physical data, what we are applying and what we are getting at the output, in order to meet steady state error and transient response requirements. So this helps us really to decide components values, verify the output responses of filter designs with respect to frequency values. So remember, even in the frequency, we use high pass filter or low pass filter. We have some kind of capacitors, we have some kind of resistor, and we are applying the input here, and we are getting output here. This is just one simple example of the one analog electronic circuit. So we need to decide these R and C values, right? So what is the cutoff frequency value? 1 divided by 2 pi RC, right? So you need to decide this R and C value. Really, you have to, in order to get the correct value, or in order to decide the correct value for this C and R, you have to do some kind of simulations, and you have to perform some mathematical analysis, how the frequency response is varying at the output. For everything, of course, we are using these transfer functions, but if you directly use this transfer function in the time domain, there are some limitations to perform this kind of output analysis. So we need to use this Laplace transform. We will see now. For example, we apply sinusoidal input to a linear system and generating sinusoidal responses at the output. So input is sinusoidal, output is also sinusoidal. It's not a non-sinusoidal. But output is different in amplitudes and phase angle. So here the output is different in amplitude and phase, not only amplitude and phase. Here the difference is also a function of frequencies. So it means the output is also different in frequencies in many cases. So now, in order to analyze this amplitude variation, phase angle variation, and frequency variation, we need a proper mathematical and graphical tool, or we need a proper mathematical and graphical analysis method, right? That is called Bode plot or frequency considerations plot. So most commonly used methods. So I mentioned here, we need the proper mathematical and graphical analysis method. So what kind of methods we are using in electronic industry? So most commonly we use Bode plot. So Bode plot, it also has different names such as approximation plot or logarithmic plot. Okay. And the second one is polar plot or Nyquist plot. This was introduced by this scientist. And third one is called log magnitude phase angle, or sorry, this is versus phase angle. So there are three methods we can use to analyze the output of the electronic systems. But of course, we do not need to go into each and every single topic, but we will study about this Bode plot. If you want to know this, the same principle is applicable in all other plots. So what is Bode plot? Bode plot is a plot of the transfer function magnitude and phase angle as a function of frequency. So again, the same thing here. Remember, I mentioned about the filter response. The filter response, what this is the y-axis we are talking about. This is the gain, right? The gain is what? VO divided by VI. That is the gain or transfer function in terms of dB. And here the y-axis is phase angle in degree. The x-axis is omega t. Omega is what? 2 pi f. So that f is a frequency. So we are analyzing this output with respect to the frequency. So in both plots, the x-axis is the same, frequency, 2 pi f. So do you know why I am using 2 pi f? This I said omega is equal to 2 pi f. So the f is the frequency of the input signal and the output signal. So here, what is this 2 pi? You should know that the technical reason behind this. So because in any sinusoidal input, any sinusoidal signal means what? So there is a positive half cycle and negative half cycle. This is one full cycle, right? And this will just repeat again and again. This will repeat again and again. This is what we are actually applying to the system. So one full cycle is ending up here, right? Starting from here and then ending up here. Can I change my pen color now? So here we call this is a 0 and this is pi half cycle, and from this midpoint until the end of the cycle is called 2 pi. You know the mathematical value of pi? Pi is equal to 180 degree. So 2 pi is equal to 360 degree. So whenever we analyze these signals, sinusoidal signals, one full cycle is 360 degree, or we can simply call this as a 2 pi. So we are analyzing one single cycle. So we are applying this input, this complete input to one system, and we are getting output. So what we are doing mathematically, we are taking one sample, that is the one full cycle, and we are performing some mathematical analysis, and that is the response it's going to repeat for all other cycles. So that is why in all the formulas we will use omega as a 2 pi f. And also when you do some kind of integration, you will also apply the limit 0 to 2 pi, and then whatever the input or the output, VO d omega t. And this VO is equal to Vm sin omega t. Vm is the peak value of the input voltage. So anyway, so these kind of things, now we do not need to go into the detail of this, how can we perform this mathematical analysis of the signals. Now we are after this Bode plot and Laplace transform. So, but you should know why I am using this 2 pi. So Bode plot is a plot of the transfer function magnitude and phase angle as a function of frequency. That is the x-axis, just before what we had seen, omega t.